the lab data from today, and I've actually gone ahead and filled in the data table with the concentration values. I had originally asked you guys to calculate these, but I've just put these in here because I've been making graphs with the data. So those are the concentrations of the crystal violet in the test tubes behind me. And I've also gone back and used some data from another year. If we go and have a look at the test tube where the reaction was happening, that's the one on the far right. It's getting a little bit more colorless, but the reaction's been going very, very slowly. I'm only up to about 28% transmittance. I don't know if you can read that dial there, but the reaction has been going very, very slowly. It's almost 130 right now. And so the data just was not going to be very good. So the next time I do this, I gotta use a higher concentration of the sodium hydroxide. It was just so slow. But that does give an indication about the effect that sodium hydroxide has on the rate of this reaction. But we're trying to ignore its contribution to the rate. So the idea is to keep it really, really high. And it's also helpful if it's high enough for the reaction to go fast, at least over the course of 10 minutes. So this calibration curve, I must have used a different wavelength as well because our percent transmittance was 18% when we first started today, I think. But the actual wavelength of light that we use doesn't matter. We just want to see how it changes as we change the concentration. We want to see how the percent transmittance changes as we change the concentration. So that's what this calibration curve was for. So here's the graph of the percent transmittance and concentration. And we can see that as the crystal violet gets more and more concentrated, less and less of that orange-yellow light passes through. More of it's getting absorbed. And in fact, it's better to graph the absorbance versus concentration. Absorbance is defined to be the negative base 10 logarithm of transmittance. So these values here, the percent transmittances, we're using transmittance, which is 1/100th of this. It's percent in decimal form. So the natural logarithm of all of these numbers divided by 100. So this right here is negative base 10 logarithm of 0.15, negative base 10 logarithm of 0.2, and so on. So when we graph absorbance versus concentration, we see that we get a linear relationship. Okay, so this is our calibration curve. Lines are really easy to model, and it's easy to get equations for lines. Technically, this line we know should pass through the origin. Google Sheets software has done a line of best fit, but we really would like a line of best fit that goes through the origin, and I'm not sure that Google Sheets can actually do that. So I've used a different software on the website Desmos, and I've typed in our concentrations in micromolar and the absorbances. And we've got a line of best fit going through the origin. The slope of this line is 0.0664. So we have a very simple relationship between the concentration in micromolarity and absorbance. So we're going to use that to follow the concentration over the course of this reaction. Again, using the data from last year. So here's the reaction data that we gathered a couple years ago, and I was trying to gather this morning, and we got a few minutes in. Transmittance was just barely creeping up little by little. But I've got the transmittance, and I've already found the absorbances. So what we can do with this data is determine the concentration of crystal violet at every moment over the course of the concentration, over the course of the reaction. And that's because our calibration curve gave us that absorbance equals 0.0664 times the concentration in micromolarity. So if we want to find the concentration, it's going to be the absorbance divided by the slope of that line, which I've hidden here. So divided by the slope of this line, 0.0664. So let's take the absorbance values and divide by the slope of the line, And that'll give us the concentration of the crystal violet. And we can do that for every piece of the data we gathered up. Okay, now technically all of these should have 3 significant figures. So for these ones right here, I can go to the 10th place, and for the other ones, I can go to the 100th place. So let me format this number. This will go to the 10th place for these ones. Sorry, the 10th place. I gotta add more formats. And these guys can go to the 100th place, actually, for their 3 significant figures. All right, so there's our concentration data. So let's graph concentration versus time. So time is going to be on the x-axis, and concentration, micromolarity, on the y-axis. Just come on down. Come on, highlight again. There's our x-axis and concentration. We're going to insert a chart. And it did the scatter plot already. That's nice. Let's move it to its own sheet so we can have a look. Okay, so this looks maybe like it's linear, but if you put a trend line on this thing, you'll find out very quickly it's not a line. So if we just try to stick a trend line on there, customize the series, add a trend line, we can see that this data is not linear. The line is beneath the data at first, then it goes above the data, now it's back beneath the data. So concentration versus time, it's a nice smooth curve, but it's not linear. Okay, so let's get rid of that trend line since we know that it's not linear. So what are some other things that we could graph to see if they are linear? Back to the data. We can also try the reciprocal of concentration and graph that versus time. So we take our data for concentration, which we've determined using the calibration curve, and now we go 1 divided by concentration. So 1 divided by that cell, and we can take that and drag it all the way down. All of these values get 3 significant figures. So these ones can go to the 10,000th place. And these ones can go to the 1000th place. And it's always the one that I want that they're not showing me automatically. Okay? Plus we can center this stuff up. Let's do that just to make it look a little bit nicer. Okay, so we've got the reciprocal of concentration. Let's see what that looks like versus time. Is that going to be a line? Insert chart. And it is not a line. It's another type of curve moving upwards slowly and smoothly. Really pretty looking curve, but not a line. So finally, one more thing we might try if we're trying to figure out the order of crystal violet, the natural logarithm of crystal violet concentration. So that's going to be equal to the natural logarithm of our concentrations, this all the way down the line. When we do logarithms, the number of significant figures becomes the number of decimal places. That's at least the case for base 10 logarithms. And so let's go ahead and adjust all of those. Format numbers. We can go to the 1000th place on all of those. Cool. So let's graph that versus time and see what we get. All right, so that's pretty. That's definitely linear. Move it to its own sheet. I can change the scaling on here. That might be good. Don't really have to, but we can customize the vertical axis and just go from, say, 1.25 up to 2.5. Okay. And let's put a line on that and see how it looks. And there we can see that that's looking quite linear. Okay? It's not perfect, but it's much more linear than our other graphs are. Okay, that's clearly an upward sloping curve, and this was a downward sloping curve. And so here we've got a nice linear type of relationship. So what does that tell us? What's the whole idea here? In the context of our chemical reaction, this is between sodium hydroxide and crystal violet. The solution's getting lighter and lighter and lighter. And the rate of reaction, we can see, the rate of reaction is slowing down over time. But the natural logarithm of concentration versus time is decreasing at a linear rate, constant rate. So that tells us that concentration of crystal violet is a first order reactant. So we can go ahead and summarize our rate law this way. Now that we've looked at our graphs, we can say that the rate of this reaction, which in general would be K times the concentration of Cv plus crystal violet cation, the purple one, raised to the N power times the concentration of hydroxide ion raised to the M power. That's our general rate law. Okay, we're going to reduce this down into a pseudo rate law, and so that's going to be K prime concentration of Cv plus raised to the N power. So we can still establish the N, let's see here, should hopefully let me go superscript. No matter. In the order of crystal violet is first order, because natural logarithm of crystal violet versus time, as we hold hydroxide concentration constant, it's really, really high, so it's constant, we're still able to establish that the reactant here, Cv plus, is first order. Okay, so we know that N is first order. And furthermore, if you really wanted to delve into it, you could go back and look at this graph and determine the slope of this line. And I can graph this one actually. Okay, so its equation is up here. Y equals negative 1.81 times 10 to the negative 3 plus 2.48. That right there is the integrated rate law for a first order reactant, where Y is the natural logarithm of concentration and X is time, and the slope is the pseudo rate constant. So this negative 1.81 times 10 to the negative 3, that's our pseudo rate constant. So back to the reaction data. K prime then is negative 1.81 times 10 to the negative 3. Okay, and if we actually wanted to figure out the true rate constant, we would have to do some more experiments to determine the order of hydroxide, but we don't know that yet. Okay.